Morning. It's my pleasure to introduce the chairman of this morning's lectures, Urs Art, from the University of Münster.
Thank you. So our first talk this morning is from Ari Shnidman, and it's about intersections of Heegner-Drinfeld cycles.
Thank you to the organizers for letting me speak. Is it not on? Let me raise it a little bit. Is that better? Okay. I have to apologize in advance. I didn't sleep very much last night paying attention to the elections in the US, so please correct any mistakes or ask questions. Okay, so this is all joint work with Ben Howard. And so let's give some setup. So the setup will be similar to the setup from Urs's talk yesterday. So X will be a curve, so smooth, projective, geometrically connected over a finite field. And F will be its function field. So that's our global field. And we're going to look at automorphic representations of PGL2. So let's let G be PGL2 over F. And so this result I'm going to describe, so for the time being, it applies only to very special automorphic representations. So I'm going to make kind of a severe assumption. I'm going to assume that it's unramified. So it's going to be a cuspidal unramified automorphic representation of G. In principle, we think you could remove this unramified assumption to some extent, but for this talk, we'll put ourselves in this simple situation, easier situation. So what does this mean? So pi lives, it's a constituent of space of compactly supported functions on the Adel group of G. So A here is the Adel ring of F. And that it's unramified, well, let's give ourselves this ring of integral Adels. So I look at all points, closed points of X, and I look at only those Adels which are integral at X. Whoops. And then I get this maximal compact this way. And it's unramified. Pi unramified means that there's a U invariant vector. Okay. The goal of these formulas involving intersections of algebraic cycles is often to say something about special values of L functions. So we'd like to say something about the L function of pi, its central value, and as we'll see, derivatives. But we'll need some auxiliary information. So we're going to give ourselves, in order to do this, a quadratic field. So we'll also give ourselves a double cover of X. And again, we're going to make kind of a severe assumption, which in principle, or hopefully one could remove, which is that this is an Natal double cover, so unramified. So F is going to be a Natal double cover. Again, geometrically connected also. Okay. Now in terms of the fields, so we have this quadratic field, quadratic extension F prime of F. And in terms of algebraic groups, this gives us a torus inside of G. So what's the torus? We get this torus, which, well, we're working in PGL2, so we'll take the restriction of scalars from F prime down to F of GM, and then we'll mod out by the GM, by GM, because we're working in PGL2. Okay, so there you can choose an embedding of T into G. More concretely, so what are the F points of T? It's just F prime cross mod F cross. So it's this torus sitting inside of PGL2. F prime is a two-dimensional F vector space, and it's acting on itself. The units are acting on itself. Okay, so, So we want to say something about the L function of pi, but what we'll actually say something about is the L function of the base change. So we'll take pi and we'll base change it to F prime. And this L function, so this, of course, this does tell us something about the L function of pi because it splits into this product. The L function that maybe we care about, and then there's a twist. So this is the quadratic character associated to the quadratic extension F prime over F. Okay, and so for this formula that I'm about to write down, due to Yun and Zhang, they'll normalize this L function in a certain way, and I won't say exactly how they do it. They just adjust it by some non-vanishing simple function of S. So this will be the normalized L function. So in particular, orders of vanishing at the central point won't be any different between these two. Okay, and so, yeah, the first theorem that kind of gives context for the results I want to describe today is due to Yun and Zhang. This is from 2015. And they give a formula for the rth derivative at the central point of this L function. And what is their formula? It says that the rth derivative of this base change L function at 1/2, that's the central point, is, well, there's some non-zero constant, which I won't write down, non-zero explicit constant. And then there's this quantity which won't make any sense right now, but they relate this special value to an intersection of two algebraic cycles on some ambient space, a self-intersection. And so it looks like this. So I haven't defined basically any of the expressions on the right-hand side. That's what I'm about to do. But what this is a self-intersection of an algebraic cycle of dimension r on, so that's this guy, T-R, pi, on a 2r dimensional stack, or some ambient space, which is this GR. Okay, and so I'll define these to some approximation. I'll define these objects. Right now, this is supposed to be a generalization or a function field analog and generalization of the Gross-Zagier formula. And in their initial paper on this work, they don't give any applications. They put out a recent paper where they remove some of these assumptions, the unramified assumptions, and they still don't quite give any applications to BSD, but they indicate that, for example, you should be able to use this formula to prove something along the lines of, if you have an elliptic curve over F and its order of vanishing of its L function is 3, then the rank should be at least 3. So these are the kinds of applications, and one hopes that this should have applications to general high order, high rank cases of the Birch-Swinnerton conjecture, but that's not totally clear right now exactly how that should work. Yeah, so maybe I should say, you could imagine that pi is the automorphic representation corresponding to some elliptic curve over F. Given the assumptions that I've made, they don't really exist because I've assumed it's everywhere unramified, but if you were to relax those assumptions, then, so that's a reasonable picture to have in your head. Okay, so yeah, let me explain what these spaces are. So these are certain moduli stacks of Stukas. Okay, I should have enough room. Okay, so we're going to actually just restrict to the even case because the assumptions, all the unramified assumptions that I make actually force the order of vanishing here. Force the root number to be even, and so the order of vanishing is automatically even, and both sides of this formula are kind of trivially 0. So we'll assume R is even. When R is odd, both sides are trivially 0. We'll assume R is even, and we'll choose a tuple of signs. And we'll choose it so that it's balanced. So if I sum up the signs, I get 0. Okay. And given this tuple, we're going to define the moduli stack. Okay, I should move up. The moduli stack of G Stukas. Okay. So this ambient space, this is going to be moduli stack of G Stukas of type mu. So this is a stack. This will be a stack over the ground field K, over the finite field. And it's a moduli stack. I'll tell you what it parametrizes. I mean, so really, it's a stack. So really, I should tell you what its S points are for every K scheme S. But I'm not going to do that. I'm going to do it informally and just tell you what its points are without writing all the S point notation. So it parameterizes tuples. So there's going to be a bunch of data. So it parameterizes tuples where what are all these data? So each of the EIs, these are rank 2 vector bundles. On X, on our curve. The Xi's are just points. There's this J is an isomorphism, so we're going to require that this last vector bundle, its Frobenius pullback is isomorphic to E0, and so J is going to be such an isomorphism. Let's write it like this. So this is the K linear Frobenius here. Maybe I should write it the other way, but okay, this is fine. So J is such an isomorphism. And what's the relationship between all these vector bundles and the points, and what are these Fs? Well, whoops. So this is going to be really a sequence of rational maps between these vector bundles. So that's what each of the Fi are. These are rational maps. F1, F2, Fr. And what we're going to demand is that each of these rational maps, they're actually an isomorphism away from the point xi. So F1 is going to be an isomorphism away from x1. Okay, so we're going to demand that it's actually a well-defined morphism if I look away from xi. And moreover, that in one direction or the other, it's in fact a morphism and its co-kernel is rank 1 skyscraper sheaf. So let's write that. So this is Fi. So extending, either Fi or its inverse will extend to, so either Fi itself extends to an actual morphism, or Fi inverse extends to an actual morphism going the other way. Which one it is depends on the sign. So this is if mu I is 1. This is if mu I is -1. So the signs are telling you which direction it goes. And we further demand that the co-kernel of this morphism is a rank 1 skyscraper sheaf. So, okay, with co-kernel. Supported, well, I mean the co-kernel, because it's an isomorphism away from xi, it's supported on xi, and it's a rank 1 skyscraper sheaf. So if you imagine these vector bundles as being, you have your curve, and over each point on the curve, your vector bundle, you can think of it as a lattice or like a rank 2 lattice, and you just have an embedding of lattices at each point, and at most points it's actually an isomorphism of lattices, but then at this one point xi, it's an index p, index q embedding of lattices, and not actually an isomorphism. Okay, so this is what this space parametrizes, tuples like this. This is a Stuka, except we're also going to look modulo twisting. So modulo twisting by pick x. So this entire data, I can just twist everything by a line bundle, and I want to identify two such data. But if they differ by a twist. And it's because we're working with PGL2 and not GL2. Okay, so this is some elaborate functor. I didn't really quite define it as a functor, but one can. And it turns out it's somewhat, or relatively well behaved. Whoops. So for us, what we'll want to know just is that it has some geometry, so it is a Deligne-Mumford stack. It's very big. It's not of finite type, but it's locally of finite type. And its dimension is 2r. So this is due to Drinfeld when r is 2, I think. And in general, I mean, you can also do this for GLN, and in general, it's due to Warshawski. Okay, why do we care about this stack? How is it relevant to automorphic representations? Well, the first way to see that it could be relevant is let's actually evaluate this functor at some scheme. Let's evaluate it at k bar. So let's ask what the k bar points are, and let's even just do it for r equals 0. So if r equals 0, then I have one vector bundle. I have no points, no maps. I do have an isomorphism of that vector bundle with its Frobenius twist. So in other words, I'm classifying vector bundles that are defined over the ground field, over K. And so in this, we could write as follows. And this is my U, I guess, my PGL2 of O. This double coset also parametrizes rank 2 vector bundles defined over K. And so here you start seeing the connection with automorphic representations a little bit. There's an even, more direct connection. The Hecke algebra, the spherical Hecke algebra, acts on this space, or really on its cohomology. So that's the other relevant bit. So let's write that. So if I write down the spherical Hecke algebra, so these are bi-invariant functions on G of A. I claim that this acts on the cohomology of this stack. And okay, let me not go into all the details, but just this.
Oh, sorry, the maps go. What is that?
Oh, Q.
Q.
Yeah, I could.
It would be O.
Yeah, no, yeah.
O is Q.
Oh, no, yeah. Yeah, we could do C also, but we can just do Q. Okay, so right, so H has a Q basis. I mean, this is an algebra under convolution. It has a Q basis given indexed by effective divisors on the curve in the same way that the Heck algebra over a number field, the Heck algebra is a Q basis by these TNs, one for every integer. So let's give ourselves this basis. So for D varying over effective divisors on X, and I'll just show how FD, this basis element of the Heck algebra, acts on GR. Somebody needs to come up with a better way of saying out loud GR, because it just doesn't sound very good. But so if somebody has a suggestion, let me know. Okay, so we'll just do it as we do over number fields with the usual Hecke correspondences. I'll write down a new moduli space, a new moduli stack, this one corresponding to this Hecke operator, FD, and I'll write it as a correspondence. And once I have such a correspondence, then I can pull back, intersect, push forward, and I'll have an action on all the cohomology groups of GR and the Chow groups also. So what is this correspondence? This is going to parameterize, and this is really exactly like the number field situation. It will parameterize D isogenies between Stukas. So what does that mean? So it's going to parameterize diagrams that look like this. So D isogenies of G Stukas. So meaning, what is a G isogeny? A D isogeny. So here's one Stuka, here's another. So a D isogeny would be maps between them that make the diagram commute. Phi0, Phi1. So actual morphisms of vector bundles. And yeah, Phi r, its Frobenius twist should be Phi0, such that this diagram commutes, and such that so we want it to be a D isogeny, so it should be an isomorphism away from D in each column. And in fact, the degree of the divisor given by the determinant should exactly be D. So the extent to which it's not an isomorphism at points above D should be governed by the divisor, D. So another way of saying that is just that the divisor of this section, det phi I, of the appropriate line bundle is D. So these are just maps of vector bundles, and we're demanding that the failure for them to be an isomorphism in each fiber is governed by this divisor D. Okay, so this is similar to the number field situation, and you get an action of the Hecke algebra on, for example, Chow groups and cohomology. Okay. So that's the ambient space, and why it's a little bit of why it's relevant for automorphic forms. There are even deeper reasons having to do with Galois representations. What about this cycle, St-Tr? So now we want to define that. Okay. Right, and of course, here too I should be modding out by twisting. Everywhere I'm going to be modding out by twisting, and I will always forget it, presumably. Okay. So this cycle, St-Tr, so this is going to be T Stukas. So we're going to do something similar just for T, which we think of as GL1, more or less, but for the quadratic extension. Okay, so what should it parameterize? It also will be a stack parameterizing tuples, and it's GL1, so it will be line bundles this time. And otherwise, it's similar kind of data. Give it a different name. So it's the exact same kind of data, but with line bundles. And so these line bundles are on the double cover now. And so these points are also on the double cover. And otherwise, it's the same kind of thing. And now, again, we'll mod out by twisting. But we're only going to twist. I mean, we don't want to twist by, well, we could, I guess, twist by line bundles on x prime. But we only want to twist by line bundles which are pullbacks from x, because we're on PGL2 over x. So modulo pick x. I mean, this acts on this kind of data by pulling back your line bundle and then twisting on the double cover. OK. So this is a better behaved stack. This is, well, you have this map from TR to R copies of the double cover. This map just remembers the legs. So it sends all of this data to just the legs of the places of modification of the Stuka. And this map, do I want to give it a name? No. So this is, it turns out, a finite étale map. What that's saying, I mean, roughly speaking, the reason is this data here is actually almost determined just from the points of modification. It is determined from the points and a choice of the initial line bundle L0. When you're working with line bundles, these modifications where the co-kernels rank 1, what you're really doing is that you're just twisting by that point, or maybe negative that point. So all these other line bundles are determined from L0, and because you're demanding that there's some Frobenius invariance, there's really a finite choice for what those L0s could be given the points. And you can work out this is actually a finite étale map. And so what you learn is that the dimension, one thing you learn is that the dimension of TR is R. It's R dimensional. And also, this is of finite type. It's étale over something of finite type. So this is a much better behaved stack. It's not as big, not as crazy as GR. Okay. Question? No? Okay. Okay. So right now, this has nothing to do with Shtoji, but we can map. We can map this space Shto-T to Shto-G just by pushing forward. So we would send all this data. I'll just write it informally to, well, you push forward, F, L0, L1. And you push forward the points, and so on. F, remember, is the double cover. So if I push forward a line bundle on x prime, I get a rank 2 vector bundle on x, and this gives me this map. Okay, and so then we'll define this guy, TR. This will be the push forward of the fundamental class along this map. Okay, this is awkward notation, but I'm pushing forward the fundamental class of the stack. Okay, you need to. There's in the Yunjing paper, they work out some of the issues with intersection theory and Chow groups of stacks, and so you need to make sense of this. But this is something that you can do. More or less, this is the cycle inside here, which is just the image, almost, of this map. Yeah. Okay, and then I mean, the one last thing is in the formula, there's a pi, and so I won't define this rigorously. This is actually very hard to make precise sense of what this means, but morally speaking, it's the pi isotypic component. Oh, I mean, I should say, this lives in the Chow group of G R. And this is the pi isotypic component of this cycle that we just created. And what does that mean? Well, the Heck algebra acts on the Chow group, and pi, it's this automorphic representation, it has a character, the way it acts on the spherical vector, and this means you project onto the part of the Chow group on which the Heck algebra acts as that character. Very roughly, but to make this precise, it's much harder. Okay. So that's the formula, and so this is the Higner-Drinfeld cycle. These are kind of analogs of Higner points, are higher dimensional analogs of Higner points in the number field setting. The point is that these shtukas coming from T, these are CM shtukas in some sense, in the sense of Urs's talk, and so these are the appropriate kind of objects where you expect maybe you can, their geometry will tell you something about special values of L functions. Okay, what time is it? So the question we're going to ask is, the Yun-Zhang formula is a Gros-Zagier type formula for higher order derivatives. In the classical and the number theory world, right after they proved the Gros-Zagier formula, there was a Gross-Konen-Zagier formula where they give a formula for the intersection of two different Higner points coming from two different quadratic fields. And so that's what we'll try to do. We'll ask, what happens if you intersect not a Higner-Drinfeld cycle with itself, but with a different Higner-Drinfeld cycle? So what if you intersect two different Higner-Drinfeld cycles? If you imagine that because these Higner-Drinfeld cycles are detecting something about the order of vanishing, for the order of vanishing of the L function, then you might imagine that that cohomologically in the Chow group there should only be one of them. And so really what we're trying to get at in this question is, are the Higner-Drinfeld cycles, are they all the same no matter which quadratic field that I take, which is what followed from the Gross-Konen-Zagier formula. And so before Kohlhagen, it also followed from work of Kohlhagen in the classical setting. Okay, so we'll consider now two different quadratic extensions. So I'm going to change my notation. So now I'll have y's. So I have two étale still double covers. So two étale double covers. But the thing is, once you consider two étale double covers, you actually necessarily have a third. Because if I look, I guess the easiest way to see this is you think in terms of function fields. This is still f. So I have k1 over k2, and then this gives me a biquadratic extension, the compositum, and so there's this third guy in there. And so similar picture over here, there's this y3. That's just necessarily in the picture. There's actually a fourth double cover that we'll want to keep track of, and we'll call that y0, and that's kind of the trivial double cover. So that's just going to be take two copies of x. That corresponds to the trivial étale quadratic algebra, k0. Okay. Okay, and so associated to these double covers, you have all the same kind of data that I wrote down for x prime. earlier, so we have our tori. And we have Adele rings. This is just setting notation. Adele rings for each of the quadratic fields. And I'm going to use the usual coset notation. I'm about to write down some integrals. Okay. So I want to tell you the sort of the L function side of the formula that we're going to prove for the intersection of the Heegner-Drinfeld cycle corresponding to this double cover with this one. Okay, so for any spherical vector, we're going to define two different toric period integrals. We're going to define this P0, which will depend on S. And I'll integrate my spherical vector over the split torus. This is just the diagonal torus. Okay. So this is my first period integral. This is essentially just the L function of pi. Okay, there's a funny 2s there, but this is up to some ambiguous constant, because I chose here a spherical vector. I don't know how to scale it, but up to some constant. I think this is right because of the 2s. This is just the L function of pi. The second toric period integral is going to be a little bit funnier. It's not going to depend on S. It's going to be, we'll integrate the spherical vector on the third torus, this one that came into our picture for free, and we'll twist it by the quadratic character, eta. Eta is the character associated to this quadratic extension, k over k3, by class field theory. I'm integrating on T3, which I can think of as being k3 cross. So this is just the quadratic character associated to the degree 4 field over k3. Okay. Okay, and just a tiny bit of notation. We're going to define C pi of S to be just the product of these two toric period integrals. Actually, we'll conjugate the second one. Oh, maybe I meant to. No, it's fine. Okay. Well, but I want this to not depend on my choice of spherical vector, so I'll mod out by the Peterson inner product. Now I have something that actually doesn't depend on my choice of spherical vector. And we care about rth derivatives, so we're going to differentiate this. So CR pi is just going to be some scalar times the rth derivative. Valued at s equals 0. The way I've normalized things, I'm at s equals 0. Okay, and then the theorem is that this quantity is exactly the not the self-intersection, but the intersection of the Stuka, the Heegner-Drinfeld cycle associated to T1 and the one associated to T2. 1r pi this is CR of pi. So that's the formula, and this is, as I was saying, this is a higher order analog of the Gross-Kohnen-Zage formula. So this is a function field, higher order Gross-Kohnen-Zage formula. And what I want to emphasize is that in the classical setting, there's the Gross-Zage formula and then the Gross-Kohnen-Zage formulas. Their proofs are completely different. They don't have anything to do with each other as far as I can tell. And the Yun-Zhang proof of the higher order Gross-Zagier formula, it follows this relative trace formula approach of Jacquet. And the point is that you can use that relative trace formula approach to unify both results, and you get a unified, there's a way to prove the Gross-Zagier formula using this relative trace formula. So the proof, which I'll go into a little bit, so we have time, goes via Jacquet's relative trace formula. So somehow in the number field setting, it's not obvious that the two formulas are related or have a common source, but in the function field setting, you can show this. Okay.
So part of the Gross-Zagier is you're also getting Fourier coefficients of half-integral modular forms.
Yeah.
So you don't get that in
Yeah. Yeah, I don't. It'll be. There might be some. Yeah. There might be something like that, but yeah, I don't. Is there a theory of?
That's wild. Maybe that's why we're here.
Yeah. I don't know what kind of theory there is over a function field of half-integral modular forms. Yeah. Okay. So what are some consequences? So I mean, again, we cared about this quantity because it carried the value. Part of this quantity is the derivative of the L function. So we got a non-vanishing criterion. So the criterion says that this intersection is 0 if and only if. So if and only if. We would like it to just be about the L function, but there are really 3 L functions that are in this picture. So if and only if the rth derivative times the 2 twists, the central values of the 2 twists, if that product of L values vanishes. So here, each chi I is the quadratic character associated to ki over f. So these are the original 2 quadratic twists for k1 and k2. Yeah. Right, and so one interesting situation is when you choose the twists so that the order vanishing is 0, and if you're in the situation where the order of vanishing of L pi is exactly r, then this is saying that these cycles aren't 0 and vice versa. If you knew that this intersection was not 0, then you would have that the L value is not 0. The rth derivative is not 0. Okay. Now what about this question of comparing the 2 cycles? The Higner-Drinfeld cycle for T1 and the Higner-Drinfeld cycle for T2. So this is the next corollary. And unfortunately, we would like to say that the 2 cohomology classes are collinear, as they are in the number field setting. But we can't quite say that. What we can say is that a certain determinant, a 2x2 determinant of height pairings, of intersection pairings, vanishes. So if I consider the 2x2 determinant, Ti, Tj, pi. So here, I and j are just between 1 and 2. This 2x2 determinant vanishes. What's the proof? The proof is that you apply all formulas that you know relating any object in this picture. So you apply the Yun-Zhang formula, our theorem, and then Waltz-Bourget's theorem, which will show Waltz-Bourget's theorem on the r equals 0 case, the actual special value, because you have that third toric period integral in there, which will come up. Okay, and so you'd like in the Gross-Konenzage story, the classical story, they do this, and then they conclude, because of the positive definiteness of the Neuron-Tate-Height pairing on the Jacobian, that in fact the two Higner points for T1 and T2, that they are collinear. We're now working we're looking at the intersection pairing in high codimension on some high dimensional stack over FQ. We don't know those kinds of properties, this kind of positive definiteness. So this doesn't imply, as far as we know, that these two cycles are collinear, but I would say it heavily suggests that they're collinear. And in their most recent preprint, Yun and Zhang announced that they have a proof that these cycles are collinear, a different proof, going through some kind of Euler system argument. Okay, and then maybe last corollary I'll write down, just to make things a little bit more concrete, is the R equals 0 version of this formula. And this is maybe the one result that you could probably port to the number field setting. This result already exists in the literature in some form, I think, in the number field setting. So this is the R equals 0 case. In the Gross-Age, the Yun-Zhang formula, when you look at R equals 0, you were supposed to recover the Waltz-Bourget formula. And so here we will recover a certain equality of toric period integrals. Okay. And I think if you look in papers of Konen, maybe Konenzage, predating the Gross-Konenzage formula, you will see formulas that look somewhat similar to this. Yeah. So when you unwind everything, this is actually what the R equals 0 case is saying. Okay. Let's see. A little less than 15 minutes. Okay, so I'll say a little bit about the proof. It goes through the relative trace formula approach of Jacquet. And I'll start actually, I won't assume anybody is familiar with relative trace formula, but the beginning of any approach using a relative trace formula is to compare certain double cosets. So I'll start with just some algebra, which compares certain double cosets. So for this, we'll talk about quaternion embeddings. And for this, I'll work over any field. This is just some cute algebra. So F is a field. K1 and K2 are quadratic étale, quadratic F algebras. And it's important that I allow the split case, as we'll see. That's why I'm not saying quadratic fields. And we do the usual thing. We form the biquadratic fellow. So you have this picture like before. You can think about what this picture means in the split case, when one of K1 or K2 is split. And then we again have K0, the split guy. Okay, so quaternion embedding, this is a definition. Is a triple B alpha 1, alpha 2. So I've fixed my two quadratic algebras at K1 and K2. And a quaternion embedding is this triple where B is a quaternion algebra over F, and alpha 1 is an embedding of K1 as algebras into B, and alpha 2 is an embedding of K2 into B. Okay, so there's a notion of isomorphism of triples, equivalence of triples. That's kind of what you would think. I won't write it down. And there's also the notion of regular triples. So think of this as like non-degenerate triples, so that will mean, so this is regular if I look at the span of the images of these two fields, that I get the whole quaternion algebra. So I want to avoid degenerate situations. Okay. and I want to classify these triples. So there's a neat way to classify them. There's an invariant attached to these triples that completely classifies these things. So given a triple, B alpha 1, alpha 2, well, what we can do is we could define vector space isomorphism from the biquadratic guy to the quaternion algebra just by sending x1 tensor x2 to alpha 1 x1 times alpha 2 x2. Because it's regular, this is an isomorphism of vector spaces, not of algebras. And then I can pull back the reduced norm, which is this canonical quadratic form on B. I pull it back to the biquadratic. And here's a computation that you can do. The reduced norm of, this is supposed to be an alpha, of a vector, alpha of x, you can compute that this equals the following expression. So this is for all x in K, the biquadratic field. Here, so there's a unique C that makes this true for all x. This is in K3, and this has trace 1. So you can check that there's a unique such C. So here, tau 3 is this, is the automorphism of K, whose fixed field is K3. Okay, and what we show is that this isn't too complicated once you write down this association. So, I mean, associated to this triple is this invariant C, and this actually gives a bijection between isomorphism classes of triples. Oh, so yeah, we're going to let Q reg K1, K2 to be equivalence classes or isomorphism classes of regular triples. And then the theorem is that these classes are in bijection with trace 1 elements of K3. And the bijection is given by this invariant. K3 such that the trace is 1. Okay, and maybe for the degenerate case, maybe I should say it's in K3 cross. Okay, and so what's a corollary of this? I want to say something about double cosets. So as a corollary, let's suppose K1 is not equal to K2, which is the setting in our theorem. The first thing is that already in this picture there are double cosets hanging around. One way to parameterize all possible quaternion embeddings of K1 and K2 is just to fix embeddings for each possible quaternion algebra. So for each B, a quaternion algebra which admits an embedding of K1 and K2 into B. So this just means it admits some embedding. I'm not choosing one particular right here. You just look at the double cosets. And this, if you think about how you would parameterize these equivalence classes of triples, it's exactly parameterized by these kinds of this double coset for any given B. Oh, whoops, quaternion algebra is B. And what the theorem is saying is that this is in bijection with trace 1 elements. Okay. And now you can do something cute now. You can take our tori T0, T1, T2, and T3 as before. you can apply this theorem to K1 and K2. The third quadratic field in that case is K3, just by definition. But you can also apply the theorem to K0 and K3. In that case, the third quadratic field is K3 again. And you get an immediate comparison of double cosets because they both are parameterized by trace 1 elements of K3. So the corollary is, if you define these tori as before, then, okay, the regular triples for K1 and K2, these, oh no, that's not right. Right. I can look at the K0, K3 case. In that case, there's only one quaternion algebra that shows up because you have a split quadratic algebra. It can't embed in any quaternion algebra other than the split one. So I get that these double cosets are actually just in bijection with this set of trace 1 elements. Because there's no other quaternion algebra that's contributing in this disjoint union. And now if I consider K1 and K2, well, then there are plenty of quaternion algebras that are contributing, but at least you have an injection like this. And so the point here is that this K3 is a common K3 for the two pairs, T0 and T3 and T1 and T2. So you get a canonical way of comparing double cosets this way. Okay. So that's all set up for the relative trace formula, which I don't have time to go into. But basically the idea is you now want to geometrize this bijection in a certain way. Yeah, and I don't have time to go into that. I was going to, but so I think I'll stop here. Thanks.
Thank you very much. Are there questions or comments? So I have a question. In the Jun and Chang, the formula is that you have to compute this intersection product and that it equals the rth derivative.
Yeah.
But in their proof, they don't really compute the intersection product. They don't count points. Yeah. What about your proof? Is that you said it's similar in nature, so you also don't compute?
Yeah.
You don't count?
So the thing is, they actually are counting points in some sense, but they're using like the Lefschetz trace formula to do it for them. They're counting. You can interpret that intersection pairing as counting points on some certain auxiliary stacks. And so yeah, okay, I don't know whether or not you call that accounting or not. I don't know, but it's ours. Ours is a similar kind of approach. We have to define more general kinds of stacks. Although in our case, because K1 is not equal to K2, the stacks are more well behaved, and they're actually not stacks. They're almost always schemes, and so things are nicer in some sense, which I think is a lesson. Like it's actually easier to prove this kind of formula, and so it might be when you go to higher rank situations, it might be the first thing to try is to maybe not try a self intersection, but just a genuine intersection.
Are there further questions? Okay, then thank you again.
Yeah.
They don't evaluate them, so they use the lectures.
Yeah.
But they don't evaluate.
Oh yeah.
So welcome back. The second speaker of this morning is Andreas Maurischat from Heidelberg, and he will speak on algebraic independence of period coordinates of tensor powers of Drinfeld modules.
Yeah, thank you.
Please.
And I would like to thank the organizers for this very nice conference and for letting me speak here. And yeah, I shortened the title here a bit, so it's just periods of T modules. That's what I would speak about. And I will tell you the goals of the talk in a minute. But before that, I want to tell you some notation. Yeah, the usual notation that we have in that setting is, we have K is an algebraic extension of FQ theta, and we have an infinite place, and the completion K infinity, and the completion of the algebraic closure C infinity. Then we have an extra variable T, polynomial ring in FQT, and the Tate algebra in T, which are the power series converging on the unit disk. Yeah, and I mean this algebra, Tate algebra contains all the rings I mentioned above. And yeah, we have the usual twist and the inverse twist on the Tate algebra, given by raising the coefficient to the qth power and respectively taking qth roots of the coefficients. Yeah, and T module is the usual definition, which I think already Anderson had. It's an algebraic group isomorphic to a d-dimensional additive group scheme. Yeah, so GA to the D. And we have an homomorphism phi from FQT to the endomorphisms. And I mean, to be really precise, we have to look at them as FQ vector space schemes, because then really these endomorphisms as FQ vector space schemes are given by a matrix ring, D times D matrix ring, in this Q polynomial ring K tau. Yeah, where tau is this map raising to the qth power. The usual definition, what one assumes for the T module is that so the phi T is an endomorphism in here, and the derivative of that endomorphism is then an endomorphism on the Lie algebra. And on the conditions that the endomorphism minus the scalar matrix theta is nilpotent. Yeah, that's the usual definition. And then, as in the Drinfeld case, we have a unique exponential from the Lie algebra to the T module itself, which is normalized and satisfies the functional equation that we also had for Drinfeld modules. And no. I mean the assumption is ends here. So if you have that, then there's a unique exponential, which is normalized and has the functional equation. There's no.
Uniformize always?
Yeah, the exponential is not surjective in general. I mean, but there is such a map. I mean, I think Anderson only did in the abelian case, but in Hartl-Juschka's paper, you can read it really for the general case. Yeah, and I mean the proof is more or less the same. I mean, if you go to coordinates, then you can really work out the coefficients of that function.
The exponential is not surjective.
No, that's the thing. The exponential is not surjective in general, but you still have this analytic map. And then this exponential also has a kernel, which is called the period lattice. And this is a FQT submodule of the Lie algebra. And I mean, it might be also that this lattice is really trivial, that is 0, if we are not uniformizable. But at that point, we don't care about that. And then we want to have the T motive associate to the T module. And usually one does it in that way, that the T motive is the homomorphisms from the module to GA, which has a K tau module. Yeah, so this has an action of KT, of FQT on E via the phi. And we have an action of K tau on GA, because that's an endomorphism of GA. And so that's a K tau module. And as a K tau module, you can, it's just free of dimension D. To really be that a motive in this general setting, we need a more general notion of motive. Which means that we only assume that it's free and finally generated as K tau module, but we don't assume that it's free or it's finally generated as KT module. Yeah. I mean, later at some points we do. I mean, if it's finally generated, so if that thing is finally generated as KT module, then one calls the motive abelian and the associated module also abelian. Okay. yeah, and so for T module, we don't assume the finite generatorless as KT module, but we assume the condition that there's some L that's missing here. There's some L such that T minus theta to the L applied to M is contained in the submodule generated by the image of tau. Yeah, I mean we here need the K because tau is not bijective on K, and so this thing is not really a submodule. Okay. Yeah, and so the main goals of this talk is on first goal, or one goal, is that we realize the coordinates of the periods in the uniformizable Abelian case as special values at t equals theta of some nice function. And this nice function, what I mean that they are entries of matrix phi or of the matrix phi inverse, which satisfy such a sigma equation. Yeah? So sigma of psi is theta psi, and the main thing is why we do that is the ABP criterion. I mean, originally ABP criterion is a linear independence criterion, and what I use is a version of that. So what Matt showed is that he turned it into a transcendence criterion. Yeah, and the condition is, so this matrix psi has coefficients in the Taylor algebra, satisfies such an equation where the theta is a matrix with polynomial entries, and the determinant is about power of t minus theta. And then it says that on one hand, the entries are even entire series, so they converge on the whole C infinity, and so we can evaluate them at theta. And if we do that, so we get the matrix where we evaluate the entries at theta, and the transcendence degree of the extension of k bar by that matrix, or by the entries of that matrix, is the same as the extension that we get if we extend k bar t by the entries of psi. Yeah, so that's the criterion, and that's what we want to do is really that we find those nice functions or such a nice psi that we get the coordinates as these special values, so that we can transfer questions on algebraic independence of the periods to questions on algebraic independence of these functions, which is often much easier to do. I mean, this is a technique that Matt and Zhang and whatever they used successfully. Yeah, and so the second goal, what I will do, I do this explicitly in the case of the Carlitz tensor power, where I can really then show that the coordinates of a fundamental period are algebraically independent. Okay. So for doing that, we need some tools. And one tool you already saw in Nathan's talk, namely hyperderivatives. I mean, that's the main tool that we use. So the hyperderivatives, so it's a family of maps dt to the n, and it's given by that formula. And what you should think of, so it acts on the power series or elements in the Taylor algebra. And what you think of that dtn is really 1 over n factorial dt to the n. Yes. So if you do that in over the integers, then you exactly get this formula, and you can reduce the thing mod p. So this is binomial coefficient mod p, and you get this formula. So that's what you should have in mind for these dt to the n, that they're 1 over n factorial. Also, I mean, the right-hand side doesn't make sense in characteristic p. Yeah? Okay. That's how one defines these differential operators with respect to t. And a nice thing is, if we have a series in Taylor algebra which even converges on a larger disk, so which even converges for t equals theta, so that we can expand it as a power series in t minus theta, then we get about the same formula for this expansion. Yeah, so about the same as above, just with t minus theta instead of t. And I mean, the philosophy for that rule is that the t goes to t minus theta as a linear transformation. So if you think of the chain rule in usual calculus, then the inner derivation is just 1. Yeah, that's why there's no big change. Yeah, and from that formula, yeah, we can compute the coefficients. Namely, if we just evaluate this case derivative at t equals theta, then all the higher terms vanish, and we are left with k over k ak, so just with a k. So with this higher derivatives, we can compute the coefficients of the expansion here. Also, maybe we don't know that expansion at first hand. How do we apply that? So in the case of the Callis tensor power, or C tensor to n, I don't tell you what it really is. We only need the thing here. So it is a T module of dimension n, and it has a pair lattice of rank 1. So this lattice is generated by one vector of length n. And Anthony Tagger also showed how you can get these coordinates. Namely, they start with the Anothen-Tagger function. Yeah, that's the main thing of the Anothen-Tagger function that we use now is that it has a pole of order 1 at t equals theta, and that it has a tau difference equation. And I mean, what I showed is if you take the nth power of that Anothen-Tagger function, so it has a residue of order n, so we can expand it as a Laurent series in t minus theta with order n. And the coordinates here you can get just by taking the coefficients of the negative powers, -1 and so up to -n. Yeah, and in particular, since the residue was minus the Callis period, then you get this c minus n is just minus pi tilde to the n. Okay, so that's what I already know. And yeah, from what I told you before, we can also compute these coordinates as special values. So namely, what we do is multiply omega n with t minus theta to the n. Then we get a power series. Yeah, and then we do the derivative of that power series and evaluate at t equals theta, and then we get the coordinate. Yeah, so that is already the first step. It's not yet a matrix entry at we want to, but at least I mean that's the first step in what I then proved, that namely these coordinates are all algebraically independent of k. In the case that n is prime to q, to our characteristic. Actually, if n is not prime to characteristic, then a lot of these coordinates will be 0. But I could also show the non-zero ones are still algebraically independent. Okay. Yeah, but we will stick to that case that it's prime to q. Okay. So that will come up in one part of the proof. Okay. So what we want to do is that we get this function, so the hyperderivative of t minus theta n omega n, as an entry of a nice matrix. And for that we need a little bit more on the hyperderivatives, namely another possibility to describe them. And that's quite easy. Namely, if you can take a morphism of infinity algebras, so from the power series ring to the power series ring in t and x, just by mapping t to t plus x. Yeah, and then you expand that thing as a power series in x. And the nice thing is the coefficients that you get, these f n's, are exactly the nth hyperderivative of f. Yeah, I mean that's classical knowledge about these hyperderivatives. I think you can already find it in Matsumura's book on ring theory or commutative algebra. I always don't know in which of his books it is. Okay. I mean you can also compute it directly. Yeah, if you want, do the computation and write it out, then you really get it. Yeah, but so it's a nice thing that it's a homomorphism of algebras, because it what do you get? So this D was a series with the hyperderivatives. And so if you validate that with that matrix, you just get a matrix, upper triangular, with the f's on a diagonal. Then you get the first derivatives on the upper row, and then the second, and so on, up to the k's derivative. Yeah. And so I denote that with row lower k. I always didn't know which index I should use. I mean, it lands in the k plus 1 matrices, but I use the k, which denotes the the highest order that occurs. Yeah, and from the construction, what you see is that this row k is indeed a homomorphism of C-infinity algebras. And furthermore, what you see is that it commutes with the twist and the inverse twist. Yeah, because the twist and the inverse twist, they act on the coefficients, on the C-infinity coefficients, and the hyperderivatives act on the T models. Yeah. Good. How does the proof work of the theorem I told you? Now we make a matrix. Yeah, that was a coordinate vector for our lattice. Yeah, and we made it in a matrix where we do the C minus n here, then the C minus n plus 1 here, and so up to C minus 1. And from the lemma I told you how to get these things, these are just the hyperderivatives of this function. And so this matrix is nothing else than the evaluation in T equals theta of this matrix. Just from the things that I did. And yeah, it's nicer to work with capital omega. So capital omega is tau of omega inverse. Yeah, and as I said before, it's T minus theta omega inverse. So that thing is that we have here. This matrix is really R n minus 1 omega n to the inverse. And then this is a homomorphism of algebras. We can take the inverse out. Okay. Yeah, and also from these properties that this row has, we find the following. So the omega satisfies sigma of omega is T minus theta omega. That you get from the tau equation from lowercase omega. And then, you go on. I mean, here you can take the sigma out, get that side, and here you take the things out. Separate the things, so you get rho n minus 1 of t theta to the n, and you get rho n minus 1 omega to the n, so that thing. And so we have now a matrix, rho n minus 1 omega to the n, which satisfies such a sigma equation. Sigma of that thing is such matrix times that. And so we can apply this IBP criterion to these two matrices. Yeah, so theta is just that thing. And it's easy from what you see is that the determinant is t minus theta to the n squared. Because we have t minus theta n's on the diagonal, and we have n diagonal elements, so we get a t minus theta to the n squared. And and this psi is just that matrix rho n minus 1 omega to the n. And what I didn't tell you in the beginning is that omega is indeed in the Taylor algebra. And indeed, it's even entire series. Okay, so we can apply this criterion. And so for showing that these coordinates are algebraically independent, it's enough to show that the extension we get from k bar t by joining the entries of that matrix has also transcendence degree n. Yeah, and so first of all, the field generated by this matrix rho n minus 1 omega n is the same as we as a extension by that matrix with the lowercase omega n. This is just because, what do they differ by? They just differ by more or less that matrix and taking inverse. Yeah, so they generate the same field. So we are left to that thing, and the next step is then to show that this thing is algebraic over that. So when we leave out the exponent n, and this really uses that the GCD is 1, that n is really prime. Because in that case, when n is prime to q, then the extension here you get that field just by taking joining omega to that field. That's also a little bit computation, which I don't want to show you. And so we are left with showing that that field has transcendence degree n over kt. So actually the field, what are the entries in here that are omega, the first derivative, up to the n minus first derivative. And we have to show that the transcendence degree is n, so that these omega up to the n minus first derivative are algebraically independent over kt. And actually, that's a totally different thing to do. What I did is showing that indeed omega and all its hyperderivatives are algebraically independent over kt. Yeah, and one often says, so if they are all algebraically independent, people say it's hypertranscendental over kt. Yeah, so that is a totally different proof, which I don't want to show you because I want to stick to that thing. And yeah, the proof here uses the special values at roots of unity, which are related to torsion points. And yeah, but actually this hypertranscendence of omega is also proved by Federico in a different methods. Okay. Yeah, so that's for the Carless tensor power. And what of that thing can we do in general? In general, we can relate the lattice to this homomorphism formal motive to C infinity t. Actually, to the tau equivariant kt homomorphisms. This is and I wrote here it's a composition of natural isomorphisms and really explicit, and I tell you how these isomorphisms, we get these isomorphisms. And the thing in the middle here, this is a subset of the Tate points of the T module, given by that the phi t action is the same as just multiplying with t. Yeah, so on this set, on the Tate points of E, we have two actions of xqt. So one just by the phi t with the tau polynomial, and one just by multiplying the coefficients with the variable t. And this is a subset where both coincide. Okay, and so the second isomorphism, that one, how do we get that? I mean, it starts quite easy. Namely, we have the T module, and we have the homomorphisms from the motive to K, and we have a natural homomorphism here. Namely, just if you have an E in here, we can map it to the evaluation homomorphism. Yeah, M is evaluated at E. And this is tau equivariant, and actually it's easy to show that this is even an isomorphism. And it commutes with the FQ2 action given by phi on E and on ME. Yeah, so you have the T action on here by phi. Okay, so this is an isomorphism of FQT modules via phi. And then we go over to the Tate points and get an isomorphism of these things. And now it's an isomorphism of FQT times FQT modules. Yeah, on one hand we have the action by phi, and on the other hand we have action by multiplication with elements in the FQT. And these commute and so on. Yeah, and then we take just the subset on both sides on which these two actions coincide. Yeah, on the left hand side it's by definition the HE, and on the right hand side what are the homomorphisms where the two actions coincide, that are just the ones which are compatible with the T actions or which are the KT linear. And that's what we get here. Yeah, and the first homomorphism you also get quite nicely. Here we start again with the Tate points of E, and we look at this map phi t minus t. Yeah, it has a kernel that was HE. We have about the same map on Lie algebra. We have d phi t minus t. And by the definition of exponential, this thing commutes. And actually, since d phi t minus theta was nilpotent, d phi t minus t is an isomorphism. Yeah, so we have no kernel and we have no co-kernel. So this is also exact. This is exact. And then, yeah, exact with commuting rows, that we apply the snake lemma. The kernels here are, actually lattice points. Actually, no, I mean, and since the lattice is discrete, it's just lattice tensor FQT. I mean, I'm a little bit vague here with the definitions. To really write it precisely, I would have to spend a lot of more time. But what you get as the kernel is that thing, and here you get that thing, and and then you have this lake lemma. You have an arrow from up here to down here, and all these maps here are maps of FQT, tensor FQT modules, and also here. And what is, so we have a map from here to here, and the co-kernel of that map, this is just the ones where both, so that's just lambda e tensor of FQT is FQT, so it's just the lattice, and this injects into HE. And then it's a different thing to show that this map is indeed an isomorphism. Also, if the exponential is not surjective, what I don't assume, you really get here the whole thing. And the idea for the surjectivity is that, it's the same thing as Hartl and Juschke have in their paper, where you join to lattice elements these sequences compatible. I mean the map you get here is really the generating series map. Towers of division points. That's what you. Okay. So that's that thing, and so you get it really explicit, the map from the lattice. So you can, if you start here with just lattice tensor 1, so you map it down, you take the inverse of that map, d phi t minus t inverse, and then you apply the exponential, and you get, and from the snake lemma you know that you're in here, and and if you work that out, for example in the Drinfeld case, the thing is really that what you get is the map which associates to a lattice point is generating series in C infinity tau t. Okay, and in the uniformizable abelian case, you can really work that all out with bases. You plug in bases and so on, and and then what you get. So we start with the motive. We have some KT basis of the motive, and if E is uniformizable, this thing is rigid analytically trivial. So we have a base change matrix gamma, which maps ME to the tau invariance of ME tensor the Taylor algebra, and what you get here is I mean, you can do that in the explicit examples. You do that really explicit, and you get a B and the coordinate system, a nice coordinate system related to the KT basis here, and an FQT basis of the lattice. And what it says, if you do that properly, then you get the entries of these bases. So they are D vectors, just as entries of special values of this matrix B d rho d minus 1 B times d epsilon the inverse, where this matrix in here is just the inverse of a nice matrix. So the inverse of that thing here, this satisfies the hypothesis of the ABP criterion, and also the prolongation of that, or d minus 1 r, also meets this hypothesis. Yeah? And in the case of the color sensor power, we just said d equals n, the b was just identity, and the gamma was the omega n minus 1, and so on. Yeah. And thank you for your attention.
Thank you very much. Are there questions or comments? Yes.
So in your last theorem, do you need to assume that E is also T-finite?
No, in that thing, I mean, for the theorem 3 that I had, I didn't assume anything on the T-module. It's really for all T-modules.
No, what just on the last slide you had there
on the
before.
The last slide, I assumed abelianess and uniformizability.
Okay,
yeah.
but you don't need it to be T-finite.
No, because I don't deal with a dual T-motive,
Okay.
but I deal with the dual of the T-motive.
I see. Okay.
Okay, further questions? All right, then. Thank you again. And we start again at 10 past. So our next speaker of this morning is Fu-Tsun. I hope I pronounced this correctly.
Yes, very nice.
And he will speak about a Sturm type bound for Drinfeld type automorphic forms over function fields.
Okay, thank you. And first of all, I would like to thank all the organizers for the invitation. It is my great pleasure to have this chance to speak here in this wonderful conference. And this is a joint work with Cecilia Amorna. And our motivation is try to study the Hicke algebra on the space of module forms over function fields in Drinfeld module form or in Drinfeld type automorphic forms. Yeah. So let me first recall the classical story. So that f be a module form of weight k for gamma 0 n c, and we write f as in its Fourier expansion c and f, and theorems of Sturm says that if C and F is 0 for 0 less than or equal to K, equal to N, K over 12 times this index, then F must be identically to 0. And if F is a cusp form, then the bound here can be smaller. Let me denote it by this by Mn, can be replaced by K over 12 times Mn, then minus Mn minus 1 over N. Oh, it's really heavy. And because the proof is very quick, let me recall it. So, in general, for n equals to 1, we just take raise f to the 12th power and divide by delta k. And this becomes a rational function on the modular curve for gamma 0 n with no pause except for infinity. So this belongs to Cj, where j is the j function. But the condition of this on these free coefficients implies that the order of this function bigger than 0. So we know that this only has poles. If this is a non-zero function, this cannot happen. So this implies f equal to 0. So, and in n, the case when n is general, you can try to take the product where this gamma I are the causal representatives of this gamma 0n in SL to Z, then this form belongs to the full level module form, but the weight becomes mn times k. So applying the same method from our assumption on the free coefficients, you get that f tilde to the 12 over delta to the mn times k. This belongs to Cj, and the order of this form bigger than 0. This implies must be identically to 0. And the case of cos form is try to consider precisely the vanishing order in here, because when f is a cos form, every term here vanishes at infinity. Therefore, you get a small bound, small condition in here. So that's the idea in classical case, very quick. And using the perfect pairing, between the space of cos forms for gamma 0n with k and the Hicke algebra, let me put C here for the space of cos forms. C, where if we take one form T maps to C1 of f in T, and where this okay, C n is the Hicke algebra generated by the Hicke operators Tm, where m the 1 inside the endomorphism ring. Okay, so this implies that we can get some information, the generators, bound for the generators for this Hicke algebra. So, see. C is not only the Hicke in algebra, but also this can be spanned by this Tm, where m is less than or equal to C. Okay. Okay, so try to study Hicke algebra over function fields, we first try to consider the similar approach to a function field case. So function field let me fix some notations. F Q theta is Russian function field, and A denotes the polynomial ring Q theta, and A plus is the monic polynomials, and we choose some level n here, and F contains in this completion at infinity, and O infinity denotes this variation ring, and we choose high infinity to be theta inverse, this uniformizer, and C infinity is the completion of a chosen algebraic closure of F infinity. Okay, that's the basic setting. And in function field case, we'll try to study the modular forms of a function field. There are two kinds of analog. One is on Drinfeld half plane. Another one is on a Maurischat tree. Okay. So let's first consider the Drinfeld module form case. For Drinfeld module form, of weight k and type m for gamma 0 n, where gamma 0 n now is congruent subgroup inside GL2A. It is a rigid analytic function. On the Drinfeld half plane with C infinity valued equal characteristic and satisfying two conditions. One is just like classical case, a transformation law. And the second one is automorphic at costs. And as a classical case, if you consider cost forms, then this becomes vanishing costs. Now, in a classical case, we have Fourier expansion, and it's the kind of a Taylor expansion at infinity. So, as in this sense, we can consider the so-called T expansion. And so fz can be written as this form. When we put f star n, Tn, where T is the uniformizer at the infinite cusp, which comes from the exponential map. But you need to take inverse. Okay. So, considering Drinfeld module form its T expansion at infinity, then and from the transformation law, we can show that f star n always vanishes unless n congruent to m mod q minus 1. So we can try use the same idea in the classical case and to get a similar result for every Drinfeld module form of weight k type n for gamma 0 n with C infinity variable, C infinity value. Suppose f star n is 0 for this 0 less than n to k divided by the weight of the delta Drinfeld discriminant function times the index of gamma 0 n in GL to A. Then we get also identically to 0. Okay. However, our original purpose is try to understand or try to know the structure of the Hicke algebra. But in this case, at least for me, it's hard to gain the information from of the Hicke algebra from this T expansion. So the problem still remains. Okay. Information. Of Hicke algebra. Yeah, that's the difference, because the Hicke algebra is generated by Tm, where m now is indexed by polynomials, but our expansion is indexed by integers. So that's the main difference. Okay. Second of all, we can consider the another analog of module forms on bracket tree, so-called Drinfeld type automorphic form. For gamma 0 n is a function on this y0 n, which is defined to be this double coset space infinity over infinity cross times I infinity to complex values. So now we are in mixed characteristic case, and where I infinity is the Ewald-Horry subgroup of GL2 O infinity. And satisfying the harmonicity condition Fg plus Fg plugging 0, 1 infinity equals to 0 equals to summation cover inside infinity for every G in GL2 infinity. Harmonicity. Okay, and you can identify this part as the oriented edges of the Maurischat tree. So this becomes the oriented edges on the quotient graph of this T by gamma 0 m. So the harmonicity condition becomes Fe plus Fe bar equals to 0 and equals to summation OEV equals to V of EV. This is for every E. E and V. Okay. So during this identification, these forms are just has another name called harmonical chain. Chains. And also, if you consider cast forms, then you have to put another condition, vanishing at cusps. And now, because these functions are complex valued, we can really use the Fourier expansion, Fourier analysis here. So, given an F inside this a space of harmonical chains or Drinfeld type automorphic forms for the congruent subgroup gamma 0 n C valued, then consider its value at these up triangular matrices. Then from its invariant property, we can write this as a summation F star RA psi. Sorry. So, yeah, AU, where this psi is an additive character, which normalized by this way. Goes to we take 2 pi I over P times the trace Q down to FP, and we take a minus A1 term here. Okay. Then the most important part is the A lies in the kernel of psi infinity. And this F star R A is a Fourier coefficient. F infinity quotient A F pi R I use U is the X psi infinity minus AX dx. Okay. And the Hart measure here is normalized so that the total volume to be 1. Sorry, pardon?
Very complex numbers.
Yes. Sorry. This is. Okay. So yeah, this type of analog is in mixed characteristic situation. So we can apply Fourier analysis here. Then from this invariant property, we can know something about the Fourier coefficients. In fact, that infinite sum is not actually infinite. It's just a finite sum. Unless degree A plus 2 less than or equal to R. And F star degree A plus 2 plus L F sum A equals to F star degree A plus 2 A for every L non-negative integers and epsilon Q cross. And because we are considering the congruent subgroup gamma 0 n, so it's invariant by this sign. And moreover, we can, if we put CMF to be the first Fourier coefficient of F acted by Tm, and we consider the 2, 1, this actually equals to Q to the power degree m times F star degree m plus 2 m. This is for every m, for every monic polynomial. So the third part, we can actually rid of the action of Hecke operators on these forms via these Fourier expansions. Okay. Oh, so maybe. So from this property, we can write F becomes some I infinity mu 0, 1 becomes Q to the minus. Sorry. There is another. Sorry. This part I forgot the Q minus L power. Okay. Plus 2 times F star 2, 0, and denote by plus summation A plus degree m plus 2 R C m F and psi m. Yeah. So the free expansion can be rephrased by this equality. Okay. So now, let me state our main theorem. Given a Drinfeld type, cusp form, F for 0n, we have F congruence to is identically to 0 if CMF is 0 for degree m bounded by 2 degree n minus 4 to B1. This is for arbitrary n is bound. Second of all, degree m less than or equal to degree n minus 2, I call B2. This is if F is a new form and n square free. Here, new form means it lies in the new space and is also a Higgs eigenform. 3, degree m is the same bound but we drop the conditions on F but put the conditions on the level. F is a PL, a P is irreducible. And the 4th one, and we can slightly generalize the third result a little bit to minus 1 if n S with S. Yeah, kind of generalize a little bit the third one to the level n having a small number of prime factors. Let me make some remark. Ideally, we usually think of these forms as analog of weight 2 module forms in the classical case. So we may guess the bound might be taken to be, for example, k is 2, and the level of discriminant function is this, and times the index. And we take the log Q. bound is on the degree of the polynomial. So that's the one guess. So, and this is kind of the genus of the corresponding Drinfeld modular curves according to the genus formula deduced by Gekeler. So,
Can I ask a quick question?
yes.
In this setting, do you have an analog of the Eichler-Silbert trace formula for the traces of the Keck operator, say Tm as a function of n? Does that exist? And is it as a sum over things like class numbers?
Yes, yes, we
So
have.
then you can presumably then get analogs of the best results for Cohen-Lenstra using your Sturm bound. That's probably an immediate corollary. I did this with Koenig in a paper in Inventionis a few years ago.
Oh,
Yeah. The whole point of if I may make a small comment, the original point of Sturm's paper wasn't to prove when a form was literally zero or not. It was really the setting of mod m or mod
yeah,
n.
yes, yes, yeah,
To have
yes.
this integral structure, it's important to point
Yes,
that.
yes.
Okay, well, I'm not telling you anything. But this is where you might have this immediate application.
Yeah, so,
If you want to know that a class number for low discriminant is not a multiple of m, where p ramifies, then you could introduce a p into your level, bound the first Fourier coefficient, which isn't zero, and then you put an upper bound on the first class number in which p ramifies where class
I
number
see,
is
I
not
see,
multiple
I
of
see.
m, and now just start counting.
I see, I see. Thank you for
I
this.
think you get this almost for free.
Thank you, thank you. Okay. Okay, so that's the situation now, and so under this and also this equals to actually the dimension of the whole space, just like I need to put cusp form here. And also, so that's one possible guess. And so comparing to this genus, the first bound for arbitrary n is too large. Yeah. So that's why we want to get small, try to get a much smaller bound here in several cases. In fact, running in computer, you can see, and also through the algorithm or argument provided by Gekeler, also the rough boutonnose, then we can show that it's actually optimal. Yeah. In this sense. And yeah, this is technical assumption. So when Sn speak, this is work in progress. Okay. So as you can see, this in this mixed characteristic case, we really have the advantage of using these Fourier expansions, so that to understand this thing. However, we don't have the original idea in classical case is more geometric, so we cannot just adapt or just using the same idea to prove here. So instead, we prove these results by using a lot of the work of Gekeler's group on the fundamental domains of the quotient graph of the root head T tree. And before going to the details, let me make some corollaries. Here we do have the perfect pairing. between the space of the cuspidal harmonical chain or Drinfeld type cusp forms. C by T goes to T. The first Fourier coefficient of T. Okay. So, similar to the classical case, we can get that T C 0 and C is spanned by Tm, where degree m bounded by Vi for I in the case 1, 3, 4. But in the second case, we assume F to be a new form and also a Hicke eigenform. So we only get the Hicke algebras on the new space generated by Em, where degree m is bounded by B2. And this is as a generator of algebra, not a vector space. So in the last 10 minutes, let me mention about the proof or the argument.
Expansions and bulk pairing is also available for higher weight cases.
Actually, in this case, because I'm considering the mixed characteristic case, so our form is C-valued, so there is no weight in this setting.
How about replacing C by CK minus 1 or something?
Pardon?
Why don't you replace C by CK minus 1 or something?
Oh, you mean considering the symmetric space? And then, yeah, you have to first introduce one idea how to define the C-valued automorphic form in higher weight over function field. But it's kind of because when you consider symmetric space, symmetric space should be over C or over C infinity. And how do you act of the matrix on that space? That's the problem. Yeah. So I'm also interested in this question, but I have no answer yet.
I guess you hope for some naive notion of differentiation that would be compatible with, like, differential forms. I mean, that would be a place to look.
Yeah. Okay. Okay. And the proof actually highly depends on the work of Gickler and that this quotient graph can be write as a union of a finite part together with some ends indexed by cusps. So the graph, for example, it may look like this way. This might cause to infinity, cause to 0. Maybe there are more. So it can be written like this. And the best part is that we can have a nice representatives of these edges. Y0 can be covered by this type of matrices. And epsilon less than 0, 1, and 0 less than or degree n minus 2. Okay? And we modify a little bit more. This can be replaced by degree n gamma minus 2, where n gamma is actually kind of the width of the corresponding cusp. So this becomes smaller than the usual n. And so we can also observe by using Iwasawa decomposition, when gamma equals to ABCD, the idea is try to replace this, find another representatives of this matrix as an upper triangular matrix. So this is actually some power of 2 degree d minus r b over d if degree c plus r less than degree d. And in other case, we can know that this becomes degree c plus r plus 1 a over c if in other cases. So this allows us to transfer this representation into our triangular matrices, and we can consider the Fourier expansion on this point. So, and so from the Fourier expansion, we get down 1. So that's how we get the B1 here. But however, this kind of using all the edges on the graph. So, and we not using that much on the harmonical chain or the structure of the graph, so that we get a much bigger bound here. So how do we reduce the bound? Second case, we assume F to be a new form, and also in the square-free level case. So here we can apply arcing linear involution on this graph. Then 1 0 is covered by this kind of matrices, and I should write n prime pi r, and where n prime divide n and 0 less than 1. Okay, so I also find suitable representatives to cover all these finite parts. But in here we use this arcing linear involution. And because if you have a Higgs eigenform, then this will become a sign. So the values of that Higgs eigenform is depends on its values on here. That's the idea for 2. But still, now we use all the edges on this finite part. So how can we remove some part because we have this homogeneity? So that's how we do for 3 and 4. Using a result by Gickler and that we can know that for f is a cusp form, then f congruous to 0 if f gamma 0 1 0 0 1 for every gamma in this means that we just need to consider every cusp form is uniquely determined by its values on these edges. Actually, they stated more that you don't need that much, but for our purpose, I just considering the values on all these edges in this part. So, and another key idea is to considering not the free expansion with respect to infinity, but the free expansion of f at 0 cusps. And 0 cusps is the arcing linear evolution acting by infinity. So we are trying to consider the free expansion with respect to these 0 cusps. And one final key lemma is that we observe that let V be the vertices represented by the identity matrices. Then for gamma in G L to A, then the distance, the minimal distance between these vertices and Wn V0 is L if and only if L minus degree n is a non-negative integer, even integer, and there are some polynomials in A with degree alpha degree beta bounded by L minus degree n over 2, such that the GCD n alpha c plus beta d is 1. Then 3 and 4, applying this technical lemma, 3 and 4 becomes just follows from whole principle. Yeah, that's the idea. So as you can see, the part we want to try to use the structure of the graph or the harmonicity of these functions to get a smaller bound. But it becomes more technical. So we are still trying to generalize or to find a better way to deal with the general case. So sorry for the late, so I'm stop here. Thank you.
Thank you very much. Are there questions or comments?
Yeah.
In your abstract, you noted that you get a criterion for elliptic curves.
Yes. And because in function field case, we also have this modularity for elliptic curves over function field. So if we take two elliptic curves with special, for example, a conductor is n and infinity, and that two elliptic curves have spring multiplication at infinity, then these two elliptic curves corresponds to two Drinfeld type cos forms with level n. So our function can be, our Stern bound can be detect whether these two functions could coincide, so that we can determine whether these two elliptic curves to be isogynous. So that's the one small application. Thank you for pointing it out.
Okay, there was another question somewhere. Did you have a question?
Then I wonder what we can say about relations of Hecke operators.
Sorry? Which relation?
And what we can say about relations between Hecke operators?
Not yet. so we just find the generator first, and other things not yet. Yeah.
Okay, thank you.
Okay, are there further questions? Then, thank you again.
Thank you.
Okay, so our last speaker of today is Dirk Basson from Stellenbosch University, and he will speak about Drinfeld modular forms of higher rank and Hecke operators. Please.
Thank you, and thanks also to the organizers for this lovely event and for giving me the chance to speak. So I used the concise title, Hecke operators in higher rank for the abstract, but a more accurate title is Drinfeld modular forms with a view towards Hecke operators. I will roughly follow the outline of just giving the setup in this situation. It's very similar to many of the other talks we've had so far. Giving some examples of modular forms. Speaking a little bit about the U expansions. And then lastly, in the time that remains, about the Hecke operators. So I should say that parts 1, 2, and 3, and a part of number 4 is joint work with Richard Pink and Florian Breuer. And they've spoken about this before at previous conferences, but Florian assured me that there are many new faces in the audience, so I shouldn't be afraid of introducing everything again and going rather slowly at the start. So I've taken the philosophy of not making many general statements of various things, but rather focusing on some concrete examples. So hopefully if you're interested in the area, you will walk away with some concrete things to play around with. Right, so let's start with the setup. So we will start with the ring. I will take FQT for simplicity, but at least in sections 1, 2, and 3, everything works for general A, and we can make the theory for that setting. This is embedded inside its fraction field F. We can embed that inside its completion at the place at infinity. So let me do this for reasons of space. And this can be embedded inside a complete algebraically closed field. So we take the algebraic closure and its completion, and we get some field C infinity that we've seen before in some of the talks so far. Then we define, similar to the way Hebeli and Gekele did yesterday, a space omega R, which will be the projective R space over C infinity, but where we remove all hyperplanes defined over this F infinity, which plays the role of the real numbers. So over all hyperplanes F, all hyperplanes H, R minus 1, thank you. Where H runs over all hyperplanes defined over F infinity. So the reason we do this is because then an element in omega R defines a lattice inside C infinity. So if we take some omega, and I will normalize each element in omega by letting the last entry be 1, because we've removed all hyperplanes H, the coordinates or the entries of such an element will all be non-zero. So I will normalize it so that omega R is equal to 1. Actually, in the papers with Breuer and Pink, we allow ourselves to normalize this to some constant which we leave unspecified, and this is for reasons of ease of presentation when we try to study questions of rationality sometime in the future. But for this presentation it will be simpler, and we lose nothing by just taking it to be normalized to 1. So the point is that then if we multiply on the left by some A module A to the R, this will be a discrete subset, a discrete A submodule of the field C infinity, and therefore we can do a bunch of things in the Drinfeld setting with it. For example, associate an exponential function, a Drinfeld module, and so on. So we also have an action of GLRF. Actually, I think you can make it an action of GLRF infinity if you wish. So the obvious thing to do would just be to multiply on the left by a matrix. So if we take gamma omega maps to, so the obvious thing would be to multiply gamma by omega just as matrices. Excuse me, I want this to be the transpose so that we have a column vector that we can multiply on the left by a matrix. However, if we do this, then the last entry is possibly no longer 1. So what we do is we multiply by the inverse of this last entry. Which I will call J of omega, J of gamma omega. So this is the last entry in the matrix product. Gamma times omega. So I will often just abbreviate this by writing gamma of omega to distinguish it from the matrix product. So one should think of this as a kind of generalization of the fractional linear transformations. For example, in rank 2, and this can happen in the Drinfeld or in the classical setting, if you multiply by a matrix ABCD, matrix multiplication would give you AZ plus B, CZ plus D, and if you were then to normalize this, because in P1 we can multiply by scalars, we would get the fractional linear transformation, and the other entry is scaled to 1. So I'm using the equivalence inside P1 over there. Okay, so this gives us an action of GLRF, and this allows us then to define what a modular form should be for some subgroups of GLRF. Okay, so the simplest presentation for this will be to say then GLRF also acts on the space of functions. Let's say f from omega r to c infinity. And actually there are many such actions. I'll define the weight k one by the so-called weight k slash operator. And this is that I act from the right on f, and what it does is, if applied to omega, we get j of gamma omega, and I can never remember if this is to the plus or minus k of gamma of omega. So modular form will be something that is invariant under this weight k operator and is holomorphic in the rigid analytic sense on omega r. I won't say more about what exactly rigid analytic means in this setting, and there's some condition at infinity as well, which I will leave until section 3 to explain properly. So if it does not satisfy this condition at infinity, we simply call it a weak modular form. So it's still holomorphic on omega r, but perhaps not as you move to the boundary. And this can be defined for any subgroup of GLRA. In general, A for any arithmetic subgroup, but in this case I will stick to subgroups of GLRA. If the following conditions hold, F is holomorphic in the rigid analytic sense. If f slashed by this slash operator is the same as f for all gamma in this arithmetic group gamma. And it's called a modular form if we also have this condition as we move towards infinity. And for technical reasons, we want this not just for f itself, but for all f applied f deltas, where delta ranges over all elements in GLRF. In practice, we only need to check finitely many of them. Right, so I guess that's enough for the setup so far. So then let's move on to a few examples. And I'll just do a few examples where we verify this condition B, and then in section 3 I will do 1 or 2 computations of the U expansion. So I think the simplest example I could think of are the so-called exponential coefficient forms. I think Gekler may have called them para-Eisenstein series at some point. So if you were to Google, you can try that. So if omega is some element in omega r, as we said, then we get a lattice AR times omega living inside C infinity, so we can associate a so-called exponential function. And the way this is defined is as essentially the obvious function you can write down, whose zeros are the elements in a to the r omega. So 0 is an element, so we multiply by z, and then we take 1 minus z over lambda, where lambda ranges over all of these elements. Now this is a function, as I said, its zeros lie in a to the r omega, which is an FQ subspace of C infinity. So if you have a function whose zeros form an FQ vector space, then it defines an FQ linear function from C infinity to C infinity, and it can be shown that it thus has an expansion, all of whose exponents are powers of Q. So we can write it in this form. And so on. So these alpha i's depend a priori on omega. So if we choose different omegas, we get different values. So they define functions that take in an omega inside omega r and give out an element in C infinity. And it can be shown that they are holomorphic in the rigid analytic sense. So the only thing we need to check is that they satisfy this holomorphicity condition. This modularity condition. So to do that, we need to see what happens if we change omega to gamma of omega and verify that this condition is satisfied and perhaps compute the weight. So let's see what happens. If we take a to the r of gamma of omega instead of a to the r times omega, well, if we were just to do matrix multiplication without the scaling by this automorphic factor j of gamma omega, then gamma defines an automorphism of a to the r. So we would get exactly the same lattice. So the difference is that this is the same as the function associated to just scaling the lattice by this j of gamma omega inverse, a to the r times omega, and this allows us to compare the coefficients in the expansions of the exponential function there and the exponential function where we've replaced it by gamma omega. Okay, so let's do the computation. A to the r. So we can write this as in this way, and there is a well-known result that says if we take the exponential function associated to a constant times a lattice, evaluated at that same constant times a variable, then we can simply pull out that constant And if you're wondering, this follows essentially from the definition of this product expansion. So if you were to compare the two, you'd see you get exactly the same on both sides. And now if we multiply this out using the power series expansion of E, we get exactly what we want. So we have J gamma omega Z. The Z to the Q term is alpha 1 of Z times J gamma omega z to the q, etc. So if we were just to focus on this one and compare coefficients, we see that j of gamma omega to the q minus 1 alpha 1 of z is equal to the coefficient in there, which is alpha 1 of gamma of omega. So we see that alpha 1 satisfies the modularity relation of weight q minus 1. And the same holds alpha 2 will satisfy it with weight q squared minus 1, and so on. So for me, this is the simplest example to illustrate how something can be modular in rank r greater than 2. Another example would be to look at the coefficient forms of a Drinfeld module. And here the computations are essentially the same. And I'm not going to do the entire computation again. Let's suffice it to say that if phi to, say, C infinity tau is the Drinfeld module associated to the lattice A to the R omega. Then we have the bunch of polynomials. For example, phi t is the polynomial t plus g1 of tau up to gr of tau to the r. And again, this Drinfeld module depends on omega. So it gives you each g1 or gi gives you a function that takes in an omega and gives you out a value in C infinity. And then a very similar computation shows that g1 is a modular form, or at least a weak modular form of weight q minus 1, and gr is a modular form of weight q to the r minus 1. So they all depend on omega. And in fact, in this representation, they also depend on t. So if you were to take a different polynomial t, like t squared, you would get more terms and the coefficient forms would be different. So in this way, you can generate a whole lot of modular forms for the full modular group GLRA. Okay, and then one more example, and this was already treated by a few people, most notably Gekela yesterday, which are the Eisenstein series for a congruent subgroup. And that would also be the one where I will compute the U expansion. Okay, so one can do this more generally. One doesn't have to take A to the R. One can essentially take any projective submodule of F to the R and general A. So the examples just illustrate the general theory at this point. And let, as Gekela said, let this be an element in F to the R where n times V is equal to 0. 0 vector. And let us assume, we can assume for simplicity that V is not itself 0. Not in A to the R, I guess. Excuse me.
But in that case, you should, NV equals to 0 is not the right condition then.
Yes, is an element in A to the R. Thank you. Then we can associate an Eisenstein series as follows. where we take the sum of the kth powers of the reciprocals, and again I use Gekeler's notation where the prime denotes over non-zero elements, so we don't run into trouble of dividing by 0. So I think these are exactly the same Eisenstein series as defined by Gekeler yesterday, except that he also went and defined the partial sums, which I won't do today. Okay, so then we can prove that such an Eisenstein series is a modular form in the sense of weight k for the modular group gamma n, consisting of matrices that are congruent to the identity modulo n. Let me phrase a slightly more general proposition. For any gamma, that if we allowed ourselves to use different lattices and this same definition, if we were to use the slash operator of some gamma on the Eisenstein series associated to V plus L, we would end up with a different Eisenstein series of the same weight, but associated to that coast set in the changed lattice of gamma. Now, yeah. And the way you do this is essentially you evaluate it at omega and realize that this gamma can either be paired with the omega, that gives you this this j of gamma omega to the k, or it can be paired with the v plus l, in which case it transforms in that way. So it follows from this definition where the gamma just goes in the middle. So associativity of multiplicativity gives you this result. Is there anyone who'd like me to write down more details? Not at this point. All right, then we can move on to some of the U expansions. So now we can really define what this property of holomorphic at infinity would be. So I should perhaps remark that most of what I've done so far was essentially known in the early 90s, maybe even the 80s, and that the really new part in the work of myself, Brouwer, and Pink is to say what holomorphic at infinity means and to compare this with an algebraic theory. Okay, so if we intersect an arithmetic subgroup with the group of matrices of this form, then we see something similar happening to what happens in the classical case, where you see that the function is simply invariant by some translation of, in our case, omega 1, or in the classical case of z. So then, for, let's say, gamma equal to 1, A1, A2 up to AR, the identity over there and 0 over there. If we apply this matrix, we see that our last entry is simply 0, 0, 0, 1 times our column vector. So that's equal to our last entry, which is 1. So our j gamma omega is simply equal to 1. So we have that f of gamma omega is equal to j of gamma omega to the minus k. Excuse me, I think that we've got the j omega now on the other side. And this is equal to 1. So we've got this kind of invariance. Or if I multiply this out, it would be f of omega 1 plus a1, a2 omega 2 up to ar omega r, and then omega 2 up to omega r are still the same. So a modular form f is invariant under the translation that sends omega 1 to omega 1 plus this this tuple a to omega 2 up to ar omega r. So our question is, can we find some expansion in terms of a parameter that is prototypical of this behavior of being invariant under such a translation? And there is one kind of canonical function we think of if we say if we want something to be invariant under such a translation, and that's the exponential function. Am I? This one? Yeah, if gamma is of this special form. So let us take the set of all elements of this form, a2 omega 2 up to ar omega r, where these elements are in this intersection. So let's say where 1a 0 id is in the intersection. That forms an FQ linear set. So in many cases it forms an A lattice, but I think for general A and general subgroups one can't quite say that. But it does definitely form an FQ linear set, and therefore we can associate.
They already a subgroup.
Yes.
Should maybe take Q prime here.
Q prime? Oh.
For pure prime, not necessarily a prime power.
Right. So it's at least an FP subspace, where P is the prime subfield of FQ. So we can associate an exponential function. Of Z, and we prove with Breuer and Pink that actually any modular form or any even gamma u invariant function has an expansion in terms of this kind of canonical parameter. So there's some careful rigid analysis that goes into showing that these expansions always exist and are unique, but ultimately this is what one would expect. So we define the parameter at infinity as, well, we would like to use this exponential function associated to omega 1. But as omega 1 goes to infinity relative to the other omegas, this exponential function goes to infinity, whereas we would like some behavior of going to 0 as you go to infinity in the same way that the parameter q does. So we use the inverse of this exponential function instead. So let us just denote this as omega prime of omega 1, where omega prime simply denotes omega, but with the first entry removed. Okay, and then we have the proposition that says any modular form can be written in terms of this parameter. So for any modular form for gamma, there exists a unique yes, that's right. Yes. for any. So let me just denote the weak modular forms like this. There exists a unique series expansion of the form Fn. These will be functions of one fewer variable, so functions of omega prime rather than of all of the omegas, and this parameter u, omega prime of omega 1 to the power n. This runs potentially over all integers, but we can then define a proper modular form as those where all the terms for negative n vanish identically. So what should this satisfy? There exists a unique series expansion that converges to f of omega on some boundary of infinity. Some boundary neighborhood, some neighborhood of infinity. And a technical condition on every and uniformly on every aphanoid subset thereof to make sure that it's actually a holomorphic rigid analytic function, where the u parameter is given by this, and we have as a separate proposition where each Fn is actually also a weak modular form for a smaller subgroup. An r minus 1 times r minus 1 subgroup. So this is a weak modular form for some gamma prime, which can be which you can get by taking the r minus 1 times r minus 1 minus. Yes.
There might happen that some weak modular forms have all the coefficients vanishing in both directions. So what do you mean for converging in some neighborhood of infinity? There might be divergence. Or maybe I do not understand how you use that.
So maybe I should say a punctured neighborhood at infinity.
There are series, and there can be infinity, maybe.
But so what I think is you need some punctured neighborhood at infinity. So even if you have even only a u to the minus 1, you still don't have convergence at infinity. So one might need some punctured neighborhood. So actually remove the boundary component, and it just converges on the complement of the boundary.
So in a weak modular form, it doesn't have to be a n greater than negative infinity. You could really have infinitely many terms in the principal part.
Excuse me, I didn't catch that.
Could you really have? That's what Federico was asking. I think. Infinitely many terms in the principal part.
Yes.
Oh, it's crazy.
Weak modular forms.
So this is really, really
Okay.
weak
This
modular
is
form.
Yeah.
weak is weak modular forms is a huge.
That's super weak. Something like that. Okay.
Thank you.
I have no idea a better name. That's
Yeah.
crazy.
Actually, someone asked me that this morning, and I did not know the answer then. But
Yeah,
thanks,
language
Ernst.
has a bounded order.
Yeah.
Wow.
So we can actually say more about these.
Infinitely weak.
No, but one usually defines the Fourier expansion first and then defines weak in terms of Laurent series. So you could have done this expansion first and then define short in terms of this finite.
So I guess if it's finite-tailed, one would be able to call it a meromorphic at infinity. And if it's not meromorphic at infinity, it's very bad. So we can actually say that these Fn's, the coefficients, are modular forms of rank 1 less, but they're only weak modular forms, and we can say that the weight in each case is k minus n. So as n goes to infinity, we get negative weight, modular forms. So we cannot in general expect these coefficients themselves to be proper modular forms in the sense of being automorphic at infinity. We do need really weak modular forms, but hopefully not infinitely weak modular forms. I think actually using results that say that the ring of modular forms is generated by certain things, one can show that one doesn't need infinitely weak modular forms. So I thought just to do one simple example of how one might compute a U expansion. So let us take n to be equal to t from the definition of the Eisenstein series. Then from the definition we have that this is equal to x dot omega to the minus k, where x runs through a set of representatives for this coset lattice V plus L. And we can break this up into potentially two terms, where the first entry, x1, is 0. x1 dot, then x prime dot omega prime. And then another part where we have x1 not equal to 0. And we have x1 dot omega 1 plus x prime dot omega prime. Now this term doesn't always show up. If v1 is not an element in A, then this term simply is not there, and it won't be a cusp form, but because it won't be 0 towards all cusps, only this one. But there will be no constant term in the expansion towards this boundary component. But if x1 is in A, then this just defines an Eisenstein series of rank 1 less, and this is a special instance of what we saw in Gekele's talk yesterday, of moving towards a boundary component, you get some partial Eisenstein series. So we could call this a partial Eisenstein series of weight k for v prime plus L prime, but this shows up only if x1, only if v1 is in A, else it's equal to 0. Okay, and for this part, I'm not going to explain, do all the computations, because I see time is running a little low. But what one does is one sees this runs over some FQ vector space, so one can use Gauss polynomials to write this in the form, the kth Gauss polynomial of the exponential function associated to the lattice generated by these elements, applied to x of omega 1. Inverse, I think. And then one can use the Drinfeld module structure to write this as a polynomial in the in our U parameter that we're interested in. If we've got the inverse of a polynomial, we can arrange so that it is actually a polynomial in U by multiplying the numerator and denominator by some high power of U, and then use a geometric series expansion. So of course, in all of this, one has to be careful of the convergence in the sense of the definition, but one can show that everything works out well. So I was hoping actually to give more details about that. But I think I'll leave that in case anyone wants to have private discussions or questions at the end or something like this. Okay, so let us move on to Hecke operators. So Pink defined Hecke operators in the algebraic sense in his papers on Satake compactification. And then we defined this Hecke operators in the analytic sense as well, and they are essentially the double coset operators that occur very frequently in many different contexts. So for arithmetic subgroups gamma and gamma prime, and some element delta in GLRF, we define the Hecke operator associated to this delta, which goes from modular forms of some weight for gamma prime to modular forms for gamma, as take some function f and send it to the sum of f slashed by delta, delta prime, let's use gamma, where gamma runs over of representatives for this coset in this double coset. So this will be a finite sum. And this is the typical definition. The first place I learned about this definition in the rank 2 classical case was in the book of Diamond and Sherman. There's a very nice treatment if you're interested in building it up for yourself. And then I looked ultimately at the book of Shimura on automorphic functions, where he gives a few more details. So those are two references that you can use to understand more about this if you're interested. So this is a very general definition, and we prove in our papers that it corresponds in some sense to the algebraic definition. I'm not going to say more about how exactly. Rather, I want to specialize to some specific situation, and this is work that I did in my thesis about 5 years back. But I used slightly different conventions from what we did, from what I did with Breuer and Pink. So I'm still in the process of translating it to the new conventions and new notation and so on. So I guess it can still be considered a work in progress. Okay, so let's just take the very simplest case where we've got the full group GLRA, and we take delta to be simply a matrix that's diagonal except for one entry, which is a prime element P. So to compute such a Hecke operator, one would ideally like a set of representatives for this space, and there's a lemma that says representatives for this space gamma delta gamma is given by the set of matrices of this form, where we've got ones except for one of the entries which is equal to P, zeros everywhere except above this entry P, and the entries above that have degree less than the degree of P, where the degree of each star is less than the degree of P. So this allows us a very concrete way of computing explicitly Hecke operators in this very special situation. Maybe I should just point out that everything up to before this example illustrates the general theory very well, but this specific example so far only really works in this example. I don't have any way of extending this to other subgroups or other A's or anything like this. I do have one nice result in this direction though, and that is how this Hecke operator acts on the Q expansion of a modular form. So we can say that Tp acts on a modular form F. So if F has the expansion as we defined before, this one, then Tp of F has the expansion so maybe I should be a little bit careful and add the weight in there. So this is a lower rank Hecker operator of weight k minus n associated to Fn, evaluated at omega prime, times some Gauss polynomial evaluated at u. So one can say explicitly what lattice this Gauss polynomial is associated to, and then
Finite lattice here. The Gauss polynomial for a finite lattice.
Yes, it will be a finite lattice.
So essentially something with the with the p torsion.
Yes, something like that, exactly. Right, so then we get this part that one can describe with Hecker operators of level 1 less, and then we have this one term where we have to evaluate u at the point p omega 1. So the way you would do this is, again, write it as 1 divided by the exponential function evaluated at p omega 1. This can be written as a Drinfeld module polynomial, so we get something that where the degree in terms of the normal parameter u blows up quite quickly. So from this, one can compute, actually I'm not going to phrase this as a proposition, I'm going to phrase this perhaps as a strategy to compute the eigenvalue of the discriminant function. So the discriminant function lives in a one-dimensional space of cusp forms, so we know it's an eigenform, we just need to somehow compute its eigenvalue, and this can be used for that because this term simply doesn't contribute, and in that term, if n is not equal to q minus 1, it also doesn't contribute, and this follows the same ideas present in Gauss and Geckler's coefficients article. So the only one that features is this g sub q minus 1, and then one can do some inductive argument on the coefficients in that expansion. So all one needs is the first entry in the expansion of delta, and there is a product formula that gives this minus delta of rank 1 less to the power q. This parameter u to the q minus 1, I'll drop all the indices, and then you have some product of a bunch of other things, but I'll write down only the first term. So if one knows the Hecker operator on the lower rank delta to the q, then one can transfer that to the finding an eigenvalue for delta itself. So I did this computation in the last few days, and I'm not 100% convinced what exactly it should be, but I think it is something like p to the q to the r. You just think minus 1 minus something. So it's something like this. I apologize. Maybe I do have my my calculations with me.
From this point of view, it's an elementary exercise.
Yes.
Nevertheless, laborious.
Yes.
But elementary, so you can do it in 2 hours.
Well, I'd hope one can do it in slightly less.
Recall delta again?
Delta is in the examples of the coefficient forms. If you take the Drinfeld module, the polynomial, the image of t, the leading coefficient of that polynomial is delta. The g sub r.
Like theta goes to
So if you were to write down the Drinfeld module for the lattice a to the r omega and evaluate it at t, you would get t plus a bunch of things, and the leading coefficient would be delta. Let's say tau to the q to the r. To the r. Yes. So that is something I studied in my thesis as well, and it is certainly if p and q are relatively prime, then one can do a simple Chinese remainder theorem type argument, and if p and q are equal, well, if q is another, so tp times tp. I think it is completely multiplicative in the sense that that would be equal to t sub p squared. And this would follow from a similar analysis that is done in Shimura. So Shimura does composites of Hecke operators, studying the complete index of two lattices inside each other. You would have to look not just at the index as an integer, but the index as some fitting ideal. And by studying that, at least with the old conventions, I could prove that it was completely multiplicative. I think everything should go through again. I just have to confer the ideas to the new conventions. I'm pretty sure it will work. Again, only for GLRA and only for GLRA and the matrices where you've got ones and a p. I'm not sure about any other cases. Okay, I think it's almost time for lunch, so let me stop.
Thank you very much. Are there questions or comments?
In the sum for the Hecke operator applied to the U expansion, what does the Gn look like when n is negative? Is it also a polynomial?
When n is negative?
Yes.
So I think the Gauss polynomials are only really defined if n is positive. Otherwise,
he assumes that the U expansion has only positive terms for the whole.
Yeah. So in this case, p is already a modular form, so there are only the positive terms.
Okay.
I guess that doesn't invalidate the question. What would the sum of the exponential functions be? But I think then one would have different ways of studying it rather than taking the sum over inverses. There might be some way of cancelling a bunch of things. There may even be some convergence issues and make it completely undefined.
So what about the other coefficient functions, the GIs? Are they also eigenforms?
Yes, that is actually something I wanted to say. So once you have this, one can do an inductive argument to get the other coefficient forms. So how this would work is that say you wanted to look at the coefficient function GI. So in rank I, this is simply the discriminant function, so it is an eigenform. Now if you were to move to rank I plus 1, what you would see is that if we hit it with TP, one thing that we need to know is that in rank greater than I, this starts with the first coefficient GI prime and then higher terms. So if we apply TP to it, it's the same as applying TP in lower rank to this first coefficient plus higher terms. And by an inductive hypothesis, this will be some eigenvalue times GI prime. Now, if we took TP minus this lambda and applied that to GI, we would get something whose constant coefficient is 0, and then we have higher terms. And this can only happen if the image, which is a modular form, is a cusp form. But there are no cusp forms in rank greater than I of weight q to the I minus 1, and therefore it must be identically 0. So Tp of gi is equal to lambda times gi. I should just acknowledge Yusuke Sukagawa, because he wrote me at some point and came up with this argument independently as well. Yes.
So since we're using a language of weakly holomorphic or weak modular forms, have you or other people considered a generalization of the Eisenstein/Poincare type construction, where you take the trace of like negative exponentials, because then you would get poles, you would get non-trivial principal parts? That's question part A. Part B is, if A is yes, then maybe this has been done, but couldn't we also substitute in negative exponentials by an analog of the Whittaker functions? Because then you'll get cross forms.
Yeah, so unfortunately I don't know yet what Whittaker functions are, but for part...
Negative exponentials, you can get like 1 over delta for free as a Poincare series by summing up the reciprocal of your exponential function. I mean, that has to be what happens.
But regarding part A, I did at some point try to construct an example of a Poincare series. So these things do exist in rank 2, but I had quite a bit of trouble getting anything good in higher rank. I can't quite remember what the reason was now. I think it has to do with in rank 2, if you subtract 2 terms from each other, there's a natural determinant that comes out. Whereas in higher rank, it is a bit more wild, and you and things don't match up as nicely as you would like. That doesn't mean there isn't anything. It's just I haven't found any yet, and I don't think anyone else has.
So Kloosterman sums, they must. So you have a rank 2 Kloosterman sum, and maybe this is where the problem starts to come up.
I don't know. I don't know if anyone else might know better than I. No. Well, maybe we should try.
Okay, are there further questions or comments? Then let's thank the speaker again. And since this fits now with the coefficients forms perfectly, let me draw your attention to the poster of Yusuke Sugiyama, who investigated the integrality of the coefficient forms.